The second design methodology we would like to look at is called the cloud component model. Notice that this methodology has been developed specifically for the cloud. Unlike the service-oriented architecture, this is specifically designed after the cloud has been introduced and specifically tailored for people using. So you have, in other words, generic application modeling and design methodology is actually geared towards supporting complex multi-tier applications which are deployed in cloud environments, and it relies on logical functional decomposition of the application. In other words, once you determine the application, the requirements, you need a functional decomposition of the full entire application, such that each logical functional unit, which is loosely coupled to other units, can be mapped directly to a cloud service in a way that realizes the benefits of the clouds. So it frees the design from the restrictive constraints of a particular programming style or even architectural pattern. In other words, once you get an application, you need to decompose it into logical units, and each unit potentially then becomes a cloud service. And then the system itself, the application itself, becomes an orchestration of these units, these components. So the cloud component model, you come up with the cloud components, and then the application becomes a combine. You combine all these. Of course, there is loose coupling so that you can manage each component separately. You can do all sorts of operations on it. Right now, let's look at this methodology. It has basically 3 steps. The first step is component design. In this design, you define cloud component model for that particular application. In other words, you come up with components, and each component has the capability to become a cloud component. Obviously, you define it properly. After that, you do an architecture design where you define the interactions between the components, and then after that, you proceed to look at deployment. This is where you now assign components to cloud resources, and that could help that problem. In other words, you have a component that have got a functional interface and also a performance interface. A performance interface will help you to collect data like logs and all that stuff. Of course, each component has got an implementation, it has resources, it can also have auto scaling, right? And that's important for each of the components that come up. So notice that when you map a component into an actual deployment, you have a less complex structure, more or less, mainly because some of the functionality can be contained in one server. So that helps a lot to simplify things. Now let's start by looking at component design. This methodology was created for the application based on comprehensive analysis of the application functions and building blocks. So that's the challenge first. You have to come up with these application functions and building blocks. The methodology itself allows identifying the building blocks of a cloud application, which are classified based on the function performed and the type of cloud resources required. In other words, you should be able to do some kind of mapping between the functions and also in the cloud resources, so you don't just analyze the application's functions. They have to be cloud oriented, sort of. They should be mappable directly to the cloud, right? So each building block performs a set of actions to produce the desired outputs for other components, and each component takes specific inputs, performs a predefined set of actions, and produces the desired outputs. Components also offer their function as services through a functional interface as we saw in the diagram B in the previous slide, which can be used by other components. Then components report their performance to a performance database server. So you can see from this diagram here that we are basically defining the elements of a cloud component. So if you look at the diagram above, we are looking at an e-commerce application where we have still the three tiers: the web tier, the application tier, the database tier. The application tier is broken down into functions that have got, for instance, a catalog, buying, selling, bidding, if there is an auction, and profile, and the search engine. And if the web tier has got a web front end, of course, that's the website. And at a very high level, you can identify this. Probably is the top one is the first thing that you do. You identify the components, the functional components of your application. In this case, you need content and catalog because it's an e-commerce site for your products. And then you need to support buying, selling, and also bidding, where things are sold by auction, and also a customer profile. Right. Notice that in each layer, each of the functions has a presence in, or you can indicate it's present in each of the layers. For instance, customer profile is present on the web tier because you don't need to provide web pages for that. And then the application tier, something happens there, and also the database tier. Note that for some things like buy, sell, bid, these are functions. You probably may not necessarily need a web tier, but you do have apps in the application tier and also a database in the database tier. Right, so this easily allow you to create, to see where you use your web apps. So this is the first component design. Now, architecture design is where you take these components and see how they communicate with each other. Right. So make sure that the components have the characteristics that are good for engineering cloud applications, like loose coupling. They are not tightly integrated, they are loosely coupled. There's also asynchronous communication between these servers, as well as stateless design. So by allowing asynchronous communication between components, it is possible to add capacity by adding additional servers when the application load increases. This allows you to do that without affecting other modules, which means they are still working. They might still work while you do that. You use message queues for that's one thing that you will learn from this course, is that if you have two modules and you want them to communicate with each other in a loosely coupled way, you need a message queue. A message queue simply acts. One application produces output and puts it in the message queue. The application that requires that as input will simply collect it from the message queue, which means the module that produces output into the queue can continue working even the other one is not, because the queue is a large store, has got large storage capacity. Only when this comes online can he start processing the queue. So that's, it's not, in other words, you can even remove one component, the other one can continue to work. So that's how you do that. Also, stateless design, components themselves are stateless. They don't remember what was happening before. And by storing session state outside the components in a database, stateless component design enables distribution and horizontal scaling as well. Right. So this step is important, and all you need to do is to take the components that you have come up with here and start drawing an architecture diagram. Right. A deployment diagram is you look at application components and you map them to specific cloud resources such as web servers, application servers, database servers. And since the application components are designed to be loosely coupled, stateless with asynchronous communication, and it means you can be deployed independently of each other. Yeah, you can just deploy them independently of each other. It makes it easy to migrate application components from one cloud to another. It doesn't matter where they are located. They can be in any other cloud. It can be in Google Cloud, IBM Cloud, because they can communicate asynchronously, possibly by just using HTTP. So that's a flexible design. In other words, you can meet both performance and cost requirements, especially in a changing situation. Right, there are a few similarities between service-oriented architecture and cloud component model. For instance, standardization and reuse. So there are arguments that the SOA advocate principles of reuse and well-defined relationship between service provider and service consumer. Right, the cloud component model, CCM, is based on reusable components which can be used by multiple cloud applications. So that's a very important similarity. Also, both of them require loose coupling of services to minimize dependencies, and cloud components is based on loosely coupled components that communicate asynchronously as well. Statelessness, this applies to both components and services, right? So that's why it is natural to consider service-oriented architecture as any methodology that works for that should work for the cloud as well. So CCM in a way was developed when someone was looking at service-oriented architecture and adapting it for the cloud. Right, the differences are basically the endpoints. Endpoints are in service-oriented architectures, but in cloud components, a very large number of endpoints. There is an endpoint for each resource inside a component identified by URI, right? So for service-oriented architecture, you have very few small set of endpoints. Now messaging is done using HTTP by using SOAP, which provide prohibitive constraint to users. SOAP is an XML-based message format which is rigid, right? Whereas in cloud components, they use HTTP and REST for messaging, and you can basically design what sort of message you want. So in terms of security, service-oriented architecture has got web service security and certain standards like SAML, SAML, and other security standards, right? But CCM only uses HTTPS for security, just basic, small and stuff. It's lightweight. Whereas, of course, the other one can still use HTTPS, but it has other, levels of security. Then interfacing, service-oriented uses XML for interfacing, and they allow resources in components that represent different formats of data like HTML, XML, and so on, so on. So it's more flexible. In terms of consumption, traditional SOA service in a browser is cumbersome. It's not easy. Whereas CCM components, underlying components expose XML, JSON, and other formats which can be transferred in HTML. So with that, we end this particular architecture cloud component model.